Спасибо. Okay, so let's start our study. Well, let's continue our study of quality of polynomials. Maybe let me say a word of apology, but we may distribute the times. Yes, a word of apology for combinatorics. In fact, I don't like it more than you do, I guess. But maybe some philosophical words. Sorry. So maybe in high school they say that mathematics consists of algebra, geometry, and analysis. Yeah. But this is not quite true, because at least those three certainly stand on unequal footing, because algebra and analysis, they're just like technical tools for solving problems in number theory and physics, maybe, or geometry. Though in mathematics it happens every now and then that something appears first as a technical tool, but then it becomes an object of study valuable in itself. Well, for example, say number pi. Certainly it appeared just as a measuring tool, but then it turned out that it's a very interesting number in itself. Say L functions. Have you heard about L functions? So they appeared first in the work of just for the proof of his arithmetic progression theorem, but prior to arithmetic progressions. It was just a technical tool. But then, maybe in 100 years, in 20th century, it became one of the central objects of study. So maybe the main object of study of last century mathematics is L functions. Okay, but nevertheless, still algebra and analysis are just technical tools. And Gelfand used to say that there are three main sources of interesting problems in mathematics, namely physics, geometry, and number theory. Now, number theory in its turn also appeared first as a technical tool, although it may sound strange, because first the basic science is combinatorics. We have to count objects, and then when we count objects, we need numbers just to write down the answer. And this is how numbers appear. But then it turned out that they deserve a study in themselves. They are very, very interesting objects in themselves. But still, combinatorics is even more basic. So mathematics starts from combinatorics and from geometry. And from physics. Well, first we need to count objects. And then also, if you prefer, say, representation theory or algebraic geometry, still you need somehow to record your results. And there is no other way, essentially, than combinatorics. So nowadays, enumerative geometry is inseparable from combinatorics, and representation theory is also inseparable from combinatorics. When you write down characters, there are some objects of combinatorics. And the best way to write down a character is if it counts some objects. The best proofs are bijective proofs. Okay, so so far so good. Okay, so the whole Well, we didn't even introduce them last time. We'll introduce them now. But what did we do last time? We introduced some other polynomials R lambda of x1, x2, t, and here the length of lambda is less than or equal to n. Sorry. So this is by definition the sum over all permutations x1 to the power lambda 1, so on, xn to the power lambda n, product of xi minus t xj over xi minus xj. Okay, and then they can be expressed via some basis in this lambda algebra with new parameter t, and so we can write down this sum over mu over u lambda mu of t, some rational functions a priori, and then sure functions of x. Okay. Now, last time we proved the proposition saying that u lambda mu is a polynomial with integral coefficients, and it vanishes unless the sizes of lambda and mu are the same, and moreover lambda dominates mu. Now we proved that the diagonal coefficients, they are not trivial, and they are called v lambda of t. Maybe last time I tried to denote them w lambda, but it was a bad idea.
No, v lambda.
V lambda, great. So this is u lambda lambda t, and we calculated that it is the product of v mi of t. So here our partition lambda has multiplicities mi, and v m of t is a product of 1 minus t I over 1 minus t. So we had this some similar notation before. Okay, but somehow here I equals 0 also counts. Well, so maybe I should, I don't know. We should understand that length of lambda is exactly n, but it has some zero parts, possibly. Okay, and in particular, we had an identity, the sum over all permutations of those permutations of the product xi minus t xj over xi minus xj. Sorry. Is Vn of t, and we will need this identity later on, but anyway, I'll have to erase it. Okay, so this we proved last time. And this time, oops,
this time, let's prove some next proposition, is that R lambda is divisible by V lambda. That is R lambda divided by V lambda lies in, no, sorry. No. I forgot how to erase. Anybody remember? Somewhere. Okay, so this lies in lambda of t. And it is the desired whole little good polynomial. Okay, so the proof is, well, suppose we have some equal parts. Lambda 1 equals lambda 2 equals so on equals lambda n, but then it is strictly bigger than lambda n plus 1 and so on. Then if W in the symmetric group permutation actually lies in the symmetric group Sm, so it permutes the first m variables, then W stabilizes x1 to lambda 1, sorry, so on, xm to lambda m, and from our basic identity this, we conclude that R lambda is divisible by Vm. Okay, and then we continue the same way with all the other pieces of lambda consisting of equal entries, and so we considering all the other intervals, lambda, whatever. We find that R lambda is divisible by V lambda, and moreover, in the ratio you get the sum over cosets, sorry, by the stabilizer of lambda. So this is the symmetric group Sn, and there is subgroup stabilizing lambda, and here you get W of x1 to the lambda 1, so on xn to the lambda n. Sorry. This time I will not be so lucky. So there is no bracket here. Sorry. Product over lambda I bigger than lambda j, xi minus t xj over xi minus xj. Okay, and so well, P lambda is the sum over the cosets W of x1 lambda 1, so xn lambda n, the product of xi minus t xj over xi minus xj. Okay. Let us also denote this by star, but unfortunately I'll have to erase this streak. Well, but maybe before I erase the streak, I'll try to say something else. So P lambda at t equals 1 is what? Yeah, the product is over lambda I bigger than lambda j. So what do you get at t equals 1?
I'm sorry.
Yes.
Big or small? I know it's not much difference, but
what is big or small?
I mean, here we had I smaller than j, and here we have I bigger than j.
No, here lambda I is bigger than lambda j. Yeah?
It doesn't matter, yes? Or
Well, since our lambdas are generically decreasing, it more or less corresponds to
Yes, it is
I being
true.
smaller than j. But since we anyway consider model the stabilizer of intervals of equal lambdas, then it's just this. So what is p lambda at t equals 1? Right, absolutely. M lambda. Nice. And what is p lambda at t equals 0? Right. How do you know?
So the R lambda is your sum
Yes.
of U.
Mhm. Yes. Okay. Well, also for those of you who attended my course on affine Grassmannians, I must say that, well, if the length of lambda equals n, again, maybe less than or equal to n, then such lambdas number some g of O orbits on the affine Grassmannian of GLM. So this is some G of O orbit. And then it is known that the spherical Haker algebra, so the algebra of functions on the affine Grassmannian invariant with respect to G of O is isomorphic to polynomials in n variables. Okay, so in particular, these guys, say the delta functions of these orbits should correspond to some polynomials, to some symmetric polynomials. Okay, and also, well, we have the trace of Frobenius function of the icy sheaves of those orbits. Okay, and just let's say characteristic functions of Green lambda. Okay, so these. Well, we have to specify some isomorphism of this affine spherical Haker algebra with the symmetric polynomials in n variables. So, for example, if this goes to Schur functions, then this goes to the whole Littlewood functions, and vice versa.
I'm sorry, but how
Yes.
did we know that p lambda t equals 0 is Schur functions?
Sinuettes. How do you know?
Is the sum of u lambda mu t s mu x. So u lambda mu is 0 unless the lambda is mu. So if t is 0, then u lambda is 1.
Yes, but we don't know what about other lambda mu's. Why it can't be sum of some Schur functions?
No, but I think just from this formula, right? You have this denominator, which is van der Monde, and also have this things vanishes. You have just monomial, and this monomial we take here. And now this monomial, because the product is over I less than j, it will be x1 to the power, I think, n minus 1, x2 to the power n minus 2, and so on. So it'll be this standard guy, so we have lambda plus delta here. So it will be just most straightforward definition of the Schur functions.
Okay.
You also divide by something, but by this. But when t equals 0, you just divide by 1. So, okay. But once again, when we discussed this fine spherical Haker algebra, I mentioned this result, and now it's formulated finally, what I mentioned years ago. In particular, those things actually make sense for arbitrary reductive Lie group. Not only for GLN, but for, say, E8 or whatever. Symplectic group, there's a notion of whole little polynomials and sort of Schur functions. Schur functions are just characters of irreducibles. But there's also a notion of whole little polynomials. So they are defined in some not in this way, in some other way, but they can be defined and computed rather explicitly. Okay, so unfortunately I have to erase this, but I hope you will have this identity before your eyes. So I press here. Yeah. I do. Maybe I even can keep this identity for a while. Okay. So now the very important lemma. One for today is the stabilization property. And this is exactly the property which distinguishes P from R. So these P's, they stabilize as I add zeros to lambda, but R's do not stabilize. So the R's do not exist in the ring of symmetric functions of infinitely many variables, but P's do exist. So let length of lambda be at most n. Then P lambda over x1, so xn 0 is the same as P lambda over x1, so xn. Now the proof is rather straightforward. So we compute just by this formula. This is the sum over cosets in symmetric group in n+1 variable modulo how to say it well stabilizing in this n+1 of lambda. Okay. W over x1 to lambda 1 and so on x n+1 to lambda n+1 sorry it's the product over lambda I bigger than lambda j xi minus t xj xi minus xj and now I can close my parenthesis. And now if xn+1 vanishes, then we only have in this sum the summands corresponding to permutations W such that W of n+1 is R, well, such that lambda R is also equal to 0. Lambda n+1 is 0 by our assumption. And lambda R must be also equal to 0, and then modulo the stabilizer in S n+1 of lambda, we may assume that W of n+1 equals just n+1, and so the sum actually runs over Sn. And I mean, we get just this. Fine. So. I forgot again. What do I know?
Just move it.
Just move like this. And then. Okay, thank you. So, maybe the conclusion or claim is that the transition matrix from the sure polynomials to the Hollywood polynomials is strictly upper prime. So we already proved it because we proved that the matrix transition matrix from sure polynomials to R's for a fixed length. It is upper triangular, but the diagonal values are exactly the things we use to renorm R's into P's. Okay, so we divided R's by those diagonal entries, we obtained P's, and simultaneously the transition matrix acquired all ones on the diagonal. So it's strictly upper triangular.
Unitriangular.
Or unitriangular, yeah. Strictly upper triangular is the same as unitriangular. well, depends on context. If it were nilpotent, I would mean zeros on the diagonal. If it's unipotent, I mean it's ones on the diagonal. Fine. So in particular, P lambda is a basis of lambda of T. Okay. Now the next proposition, number 2, is that P corresponding to partition of all ones is just elementary symmetric function ER. In particular, is independent of T. Right? And the proof is straightforward again. So we may assume the number of variables is just R because of this stabilization. And then from this identity, well, just definition of PP, what do we get? S lambda is the whole of SR, right? Because lambda is just all ones partition. Yeah, and so there's just one summand, right? And there's no factor here. Okay.
I'm sorry.
Yes.
Is it the whole group or it is the identity group?
Pardon me? Where?
I mean, S lambda, it should be S lambda 1 times S lambda 2, just the identity, no? It's trivial group, not the whole SN.
No, in this case, you see, S lambda, maybe it's a bad, maybe it was a bad notation, but by S lambda, I always mean the stabilizer in Sn of lambda. Okay. Yeah, it's maybe in some other context. It's not the parabolic group with such.
Okay,
Yeah, sorry. I'm sorry. We just have one sum x1, so xr. Okay, which is er. So this was easy, and well, we will also need some other polynomial qr of xt. So this is essentially p r when the partition is of one piece, but it is 1 minus t. It's a slight renormalization pr over xt. Okay. Also, just in case q0 of xt is just 1, well, defined as 1. Okay, and well, let me try to write one more important identity. There is 1, 2, and I will need third one, but no more for today. So qr of x1, so xn, xn and t is 1 minus t, the sum from I equals 1 equals 1 to n xi to the power r, the product over j not equal to I, xi minus t xj over xi minus xj. Okay, it is just the particular case of the identity over here. Okay. Now we'll have lambda 2. This is the generating function of those QRs. The sum from R equals 0 to infinity over QR of xt times y to the r, that's just a counting function, is the product over all I, 1 minus t x I y over 1 minus x I y. Okay. So the proof is, let's say, let number of variables be n, and set z is y inverse. And then expand the product of z minus t xi over z minus xi, this thing, the right hand side. As a sum of now my English is bad. What is called simple fractions or basic fractions, or what? Простейшие дроби. How do you say it?
Reduced fraction.
Reduced fraction, really? Well, you will tell us now.
Partial fractions I saw.
Partial fraction,
No.
really? Простейшие дроби? Yeah.
But I'm not sure. I just need to try it.
But just, no. If you go to Wikipedia, простейшие дроби, and then go to English version of Wikipedia, it will tell you the correct terminology.
Yeah, but the problem is there is no
Wikipedia.
page for простейшие дроби.
Really? Okay, but
You
let's
can continue. I will Google it.
Okay. So let's assume that it's simple fractions. Just when you do first year analysis integration, you need this tool. Yeah? But when you try to integrate some rational expression, you write it down as a sum of expressions where in the denominator you have just the power of any rational function, like q.
It says the term partial fraction is used when decomposing rational fractions into sums of simpler fractions.
Yes.
So it's partial
Partial.
fractions.
Okay. Partial.
Thank you. Sorry about my illiteracy. So Q is the sum of 1 over x minus ai to the power di. Well, no, not 1 necessarily, but some number, ci. Okay? Any rational function can be written down like this, right? And these are called partial fractions. So what do we get? We get that this is 1 plus the sum over I from 1 to n, 1 minus t xi over z minus xi, product over j not equal to I, xi minus t xj over xi minus xj. Okay, so I mean, here is in z. We view it as a function in z. And then, well, this had a complicated denominator, product of some simple factors, and this has only denominators, just linear functions with some coefficients. Those coefficients are independent of z. What do we have to do to check that this is true?
I think I would believe you.
Yeah, that's the general method, that's true, but somehow if you were in your first year analysis course exam, what would you do to check that this is true? By the way, this is called the great Chinese remainder theory, right? So we just have to find the values at all those points. Right? The quotient ring of polynomials modulo the product of those is just direct sum of quotients modulo this simple.
But this case is very simple. You can just
Yes.
write.
Yes.
You,
You
you can just
So
calculate
this what
and
is-
you
is-
get this.
simple, we say. Yeah, I don't. We wouldn't argue, yeah. Okay. So this means that the product, going back from z to y, it means that the product from for all y, for all I from 1 to n, 1 minus t x y over 1 minus x y is 1 plus 1 minus t sum over I x I y over 1 minus x I y, the product over j distinct from I, x I minus t xj over x I minus xj, and hence the coefficient of y to the power r is qr of x1 xn t. Okay, and finally we stabilize and goes to infinity. Okay, now let me just go up. This. The definition, the renormalized
whole little polynomials. Q lambda of x at t are defined as certain multiples of whole little polynomials. And the factors, extra factors, are defined as the product of phi mi of t, whereas always lambda is has this exponential notation. In particular, q r of x t is nothing but the small q r of x t. Okay, and well, later on, so next time, first we will make contact with the previous whole theory. So far, it's so to say Littlewood theory. There's a Littlewood definition of those polynomials. But before, I said that there was an isomorphism of the whole algebra with lambda of t. Well, when it's specialized t to q. And the standard basis of the whole algebra, again, of sort of delta functions, of the delta functions of isomorphism classes of O modules. Yeah, it went to this basis, p lambda of xt. Okay, that this was the original whole definition of those polynomials. We will prove that those two things coincide next time, and then we'll go on with their study. In particular, we will characterize them by some orthogonality properties. Like, for example, Schur functions can be characterized. You start with, say, monomial functions, and then you, then you introduce the scalar product for which the power functions are orthogonal, not orthonormal, but orthogonal. The scalar square of p lambda is, say, some z lambda, right? Anyway, there is some element, well, defined in elementary way, scalar product. And now the monomial functions are not orthogonal at all, but when you apply the Gram-Schmidt process to them, you obtain just the Schur functions, right? Because each Schur function starts with this term, like m lambda, but then you add some smaller terms, and the result gives you orthonormal basis in this scalar product. Okay, so this ideology is very useful, and well, the culmination of this ideology was Macdonald definition of Macdonald polynomials. So they depend not only on t, but on one extra variable q, and this extra variable q is not well. So I don't know how to say this, but this t plays the role of number elements of in the finite field, which is usually called q. But there is one extra q, which has some other meaning, and there are some second quantizations or deformations of these polynomials, which depend on two variables, t and q, independent variables, t and q. And they're defined by the same process. So you define some fancy scalar product, and then you just apply Gram-Schmidt process to the monomial functions, and you obtain those Macdonald, or particular case, whole Littlewood polynomials. Okay, so they will not be, well, but that's not quite true. What I said is not quite true, because those p lambdas will not form orthonormal basis, namely it will be on an orthogonal basis, but their duals will be those q lambdas. But we'll see this like next week or something like this. So Another construction. Of Q lambdas. Well, this set fi of x1 and so on xn is by definition f. Let's go, well, given a function in n variables, you define its ith part just by annihilating the variable xi. So you just plug in ith variable equal to 0. And then the next proposition is that Q lambda is the sum over I from 1 to n of xi to the power lambda 1 ui q lambda tilde I. So it's sort of an inductive construction. So here what is the meaning? Lambda tilde is obtained by disposing of the first, the biggest part. So it starts from lambda 2, lambda 3, and so on. Just dispose of lambda 1. And ui is 1 minus t product over j distinct from I, xi minus t xj over xi minus xj. Okay. I should say recursive construction. Yeah, so you take the smaller number of variables and the smaller number of parts, like this. Well, but unfortunately now I'll have to refer to these identities, Schräg star and double star. So we said L is the length of lambda, and then V, this V was the diagonal entry of the matrix expressing R polynomials via Schur polynomials, and also there was an explicit formula for this V, which implies in particular that there is V n minus L of t times B lambda of t divided by 1 minus t to the power L. Okay. And this implies that Q lambda of x1 xn t is 1 minus t to the power L over V n minus L of t R lambda over x1 and so on xn t. and now this is equal to 1 minus t to the power L, the sum over permutations in the cosets of Sn over S and minus L, W over x1 lambda 1, x L lambda L, the product from I equal to 1 to L, the product over j bigger than I, xi minus t j over xi minus j. So this equality is just by applying our first identity to well, symmetric group m minus n L variables. I mean, you have x1 and so on, xl, and then you have xl plus 1 and so on, xn, and well, those are permuted by n minus l. So there are some important variables because lambda has length L, and then some other which don't matter much. Okay, so we get this equality, and now it will be equal to the sum over permutations in the coset by n minus 1, permutations n minus 1, w over x1 power lambda 1, u1, q lambda tilde, of x2, so on, xn, t, okay, and this way obtained by comparing well,
I think there should
yes,
be sum over all I also. No?
No, I don't think so. So just compare, well, what to say, such expressions. Well, how to say this? Expressions to the left. For q lambda and q lambda tilde when you dispose of the first part and take n minus 1 variables. Okay, and this is just what we wanted to prove. Okay, now maybe I keep this because we will need q lambda and erase the proof instead. So Ah, I
You
need to
a
create new page and
top middle green cross.
Top, middle, green, cross. Thanks. Works perfectly. Okay. Two more notations. So for a composition, alpha, alpha 1, so on, alpha n. No, it's not a composition. Well, because they can be negative integers. Yeah, but not necessarily positive integers. We set q alpha of x and t is there's the product of over parts. Q alpha I of x t, with understanding that q with a number whatever a less than 0 is said to be 0. So if any part of our partition happens to be negative, then the whole thing is 0. Again, nothing fancy. So this was number 1. And number 2 is that raising operators, such a notion also enters your last home assignment. I mean, for April, whatever, 17th or 24th. The most recent home assignment. Raising operators R, J, K, so Q lambda is U, but associated to some other partition or rather composition. So you take lambda 1 and so on, and then lambda j gets increased by 1 and so on, and then lambda k gets decreased by 1 and then so on. So j is less than k. And you see, after such operation, it is possible that you get not a partition. I mean, they are unordered, and so you will need to use this definition. Or even something from 0 could become negative 1, and then you will get just 0 by this. Okay, so the next proposition 4 says that q lambda is the product over j less than k, 1 minus r j k over 1 minus t r j k q lambda. Okay, so well, well, maybe it's not a recursive formula, but again, sort of explicit formula, because q lambda is something relatively explicit. Well, like this, and then I take products of those, and then you apply some operators, raising operators to this. Well, not really explicit, but some. Okay, so let's prove this. Yes.
What is the quotient of operators for this IJK?
What is the meaning of that? It's just a formal. You expand it as a geometric progression, infinite series, and then apply. But almost all terms will annihilate any particular q lambda. So this will make sense.
I see.
Okay, so proof. Just by induction, in the length of lambda. So for length of lambda equals 1, when lambda consists of just one part, it is just, this will be just this definition. QR, that's fine. So this is the base of our induction, and now.
And if
yes?
we apply this 1 minus RGK divided by this, we get also QR. I mean, the right hand side in the base of induction, it will be trivial, yes?
Yeah, I think only, so when we expand this, you will have certainly 1 plus some expression in raising operators. But any raising operator applied to partition with one part will kill it. Yeah,
Because K, yes.
yeah,
okay.
just because K is bigger, so I have all zeros and you get something like now for L bigger than 1, we assume that the proposition is proved for a partition with smaller number of parts, but let's view it not as a partition, but as a composition starting with 0. So we just dispose of the first biggest part like before, but we replace it by 0 to formally keep the length. Now, lemma 2 implies lemma 2 was this generating function of QRs. Yeah, it was here, but some time ago. So it implies that the sum of over all r's, q r i's, y to the power r is equal to 1 minus xi y over 1 minus t xi y. The sum over all r's, q r y to the power r. Okay, and now I will return here. So, comparing the
coefficients of y to the power r, we can express q r via q and xi, namely we get that q ir equals 1 minus xi e over 1 minus t xi e applied to qr, and e is the operator, sort of lowering operator. E qm is qm minus 1.
Okay, and it will be the well, the reason for the appearance of those raising operators.
Okay, so hence q I lambda tilde is the product from g equals 2 to L, the length, of 1 minus xi e j over 1 minus t xi e j applied to q lambda tilde, where e j q alpha that lowers the jth part is q alpha 1, so on, alpha j minus 1, and so on. Okay. Now let's consider the sum over all I from 1 to n of xi to the power lambda 1 ui q I lambda tilde. And this is the sum over all I from 1 to n of xi to lambda 1 ui, the product over k from 2 to L of 1 minus xi e k over 1 minus t xi e k applied to q lambda tilde, where we had this ui 1 minus t product over j distinct from I, x I minus t xj over xi minus xj. Okay, and now we have this equality double star. So shall I recall it, or
Maybe let me recall it here. Do you want me to recall it? Or you'd rather forget it forever? So then I will not recall it, unless you urge. Okay. It implies that q
q lambda 1 is the sum of xi to the power lambda 1 times ui. And hence the sum of over I from 1 to n of xi to the power lambda 1 ui q lambda tilde I is the product of over k from 2 to L 1 minus R 1k 1 minus t over 1 minus t R 1k applied to q lambda. Yeah, because well, we just had E, and now we replace it by R1k, because E lowers this, but R1k also raises the power of, well, increases the first thing, lambda 1. But this is exactly what happens here, right? Because so I lost one extra power of x I because it's here. Yeah, xi. There's one extra xi, so it exactly increases the power of xi, which is lambda 1, will become lambda 1 plus 1. Yeah, because there is this coefficient of ek. Yeah, you will have xi to lambda 1, but because of this, you will have xi to the power lambda 1 plus 1. And you will have this raising operator. Okay. And we're almost done. What should I? Maybe I should just go up a little bit. Like this. Now from proposition 3. The proposition 3 was this inductive recursive construction, which you hopefully also remember the previous proposition, and the induction assumption. We have q lambda equals the sum over I from 1 to n x I to the power lambda 1 ui u lambda tilde I, okay. And this is the sum over I from 1 to n x I to the power lambda 1 ui, the product over j starting from 2 less than k at most L 1 minus r jk over 1 minus t RGK Q lambda tilde I. And by the previous equality, well, it's, I don't know. We get what we wanted. That Q lambda is a product over all I, j less than equal to k, less than k, 1 minus r jk over 1 minus t r jk Q lambda. Okay, and well, expanding this, we get, as Shuai mentioned, the product over j less than k, 1 plus t minus 1 r j k plus t squared minus t r j k squared plus so on applied to Q lambda. Okay. Now, well, maybe let's stop here, and next time we will prove that those P lambdas are the ones coming from whole algebra, and introduce the scalar product. And as I said before, those sufferings somehow are inevitable, because if you want to get the characters of symmetric groups obtained by Frobenius, you cannot do this without Schur functions. You absolutely must know the theory of Schur functions. Yeah, it's a Jacobi-Trude identity, or some basic theory of Schur functions. You cannot proceed without it. And for the GGL over finite field, the role of those Schur functions is played by whole root polynomials. So you absolutely cannot proceed without developing the parallel theory, so deforming, quantizing this theory of Schur functions with an information parameter T. So I'm sorry about this, but it's inevitable. For your patience.